Welcome back, cosmic adventurers, to Wonderscope. Today, we're embarking on a thought experiment of truly epic proportions, a journey that will challenge your perception of reality and leave you breathless. We're going to explore a universe fundamentally different from our own, a universe where a seemingly simple change, the introduction of air into the vacuum of space, triggers a cascade of catastrophic events, ultimately leading to cosmic annihilation. So, tighten your spacesuit helmets, because we're diving deep into the hypothetical abyss of an air-filled universe. Let's start by grounding ourselves in the familiar. We all know that space is a vacuum, right? It's the vast emptiness that exists between celestial bodies, from the planets in our solar system to the stars in our galaxy and the countless galaxies scattered throughout the observable universe. But what does vacuum really mean in this context? It's not just empty space, it's the absence of matter, a near-perfect void far more extreme than anything we can create in our most sophisticated laboratories. In interplanetary space, within our solar system, the density might be a few atoms per cubic centimeter. In interstellar space, between the stars, it drops to about 1 atom per cubic centimeter. And in the vast gulfs of intergalactic space, it can be less than 1 atom per cubic meter. This near emptiness is not just a curious feature of the universe, it's fundamental to its structure and evolution. It allows celestial objects to move under the primary influence of gravity, unimpeded by significant resistance. But today we will change all of that. Now, for the sake of this grand cosmic experiment, we're going to introduce a substance utterly foreign to this void, air. And not just any air, but the air we breathe, a mixture of 78% nitrogen, 21% oxygen, and trace amounts of other gases. We'll assume this air has the same density as it does here on Earth, 1.225 kilograms per cubic meter at standard temperature and pressure. Imagine this air slowly filling the solar system, then the space between stars, and eventually the entire observable universe. It might seem innocuous at first, perhaps even beneficial. But trust me, the consequences of this seemingly simple act are anything but. We're about to unleash a symphony of destruction on a cosmic scale. We will start to destroy everything from here. Let's begin our exploration of this altered reality within the confines of our own solar system. In this air-filled cosmos, the dream of space travel takes on a new, frustrating dimension. Sure, you could theoretically fly a plane to the moon or Mars, but air resistance, a force we usually only associate with moving through our atmosphere, would become a dominant factor. That quick hop to the moon, forget it, we're talking weeks, maybe even months, of slow, arduous travel. And a trip to the sun, that's a multi-year endeavor, assuming your aircraft could even withstand the increasingly extreme conditions, not to mention running out of fuel long before you reach your destination. But the difficulties of space travel would be the least of our worries. The solar system, now filled with a medium capable of transmitting sound, would transform into a cacophonous nightmare. The sun, a seething cauldron of nuclear fusion, would become a deafening presence. Scientists estimate that the sound reaching Earth's surface could reach an intensity of 125 decibels, the equivalent of standing a few feet away from a military jet engine during takeoff. Imagine that, 24/7, with no escape. It would be enough to drive anyone mad. And then comes the friction. Every object moving through this newly air-filled space, from the smallest micrometeoroid to the largest planet, would encounter the relentless drag force of air resistance. Satellites, our silent sentinels in orbit around Earth, would experience a fiery demise. They would heat up, glow red-hot, and disintegrate, their fragments raining down as a deadly shower of debris. The moon, our faithful companion, would face a far more dramatic fate. The constant drag would act as a brake, slowing its orbital velocity. Its orbit would gradually decay, spiraling ever closer to Earth in a terrifying cosmic dance. And then, the inevitable, a catastrophic collision that would obliterate both the moon and Earth, an event far more devastating than the asteroid impact that wiped out the dinosaurs. But what about our planet? Earth, with its high orbital speed around the Sun, would experience an even more intense frictional heating. The atmosphere would become superheated, potentially igniting into a global inferno. Our blue planet would be transformed into a charred, lifeless husk. And the other planets in the solar system, they would share the same grim destiny, each one slowing down, spiraling inwards, and eventually plunging into the sun, consumed by the very star that gave them life. But the fiery destruction of the solar system might pale in comparison to the next act in this cosmic tragedy. Let's consider the sheer volume of our solar system, extending out to the heliopause, the boundary where the sun's influence gives way to the interstellar medium. Filling this vast region, roughly 90 astronomical units in radius, with air at Earth-like density would introduce an almost incomprehensible amount of mass, approximately 1.251 times 10 to the power of 40 kilograms, or about 6.3 billion times the mass of our Sun. This sudden influx of mass would have one inevitable consequence: gravitational collapse. The entire solar system, along with the newly introduced air, would be crushed inwards by its own gravity, forming a supermassive black hole of unimaginable proportions. To put it in perspective, this black hole would be far more massive than Sagittarius A star, the supermassive black hole residing at the center of our Milky Way galaxy, which only masses about 4 million solar masses. The formation of this behemoth within our galaxy would unleash chaos on a galactic scale. Nearby stars, like the Alpha Centauri system, would be among the first to be devoured, their matter adding to the black hole's already immense bulk. Stars farther away would have their orbits drastically perturbed, forced to revolve around this new gravitational giant. Our Milky Way would, in effect, become a galaxy with two centers of gravity, two supermassive black holes dictating the motions of stars. And these two titans wouldn't coexist peacefully. Over millions, perhaps hundreds of millions of years, they would engage in a slow, spiraling dance, their mutual gravitational attraction drawing them ever closer. The climax of this cosmic ballet would be a cataclysmic merger, an event that would release an almost unimaginable amount of energy, primarily in the form of gravitational waves. These ripples in the fabric of spacetime would propagate outwards, shaking the very foundations of the galaxy. Now, let's elevate our thought experiment to the grandest scale imaginable, the entire universe. We know that the universe has been expanding since the Big Bang, a process driven by a mysterious force we call dark energy. This enigmatic energy acts as a kind of anti-gravity, pushing space apart and counteracting the inward pull of gravity from all the matter in the universe. Currently, dark energy is winning the cosmic tug-of-war, leading to an accelerated expansion of the universe. But what happens when we introduce air into this equation? The answer is a dramatic shift in the balance of power. The density of matter would increase by many orders of magnitude, and gravity, now significantly stronger, would begin to overpower the repulsive force of dark energy. The consequences of this shift would be profound and irreversible. First, the expansion of the universe would gradually slow down. Then, it would come to a complete halt. And finally, in a dramatic reversal, the universe would begin to contract. This process, known as the Big Crunch, would essentially be the Big Bang in reverse. As the universe contracted, galaxies would begin to collide, merging into ever larger structures, igniting bursts of star formation on an unprecedented scale. The universe would become a maelstrom of activity, a fiery cauldron of creation and destruction. Countless supermassive black holes would form, each one a gravitational singularity, and these black holes would themselves begin to merge, creating even more massive behemoths. The temperature of the contracting universe would rise inexorably, climbing to unimaginable levels, far surpassing the temperatures found even in the cores of the hottest stars. The entire universe would become a searing inferno, a state reminiscent of the conditions that existed shortly after the Big Bang, only this time, it would be leading to a catastrophic end. In this scenario, the contraction would continue unabated until the entire universe was compressed into a singularity, a point of infinite density in temperature. It would be as if the cosmic film reel was being played in reverse, ultimately erasing everything that had come into existence since the Big Bang. A complete and utter cosmic undoing. But the effects of an air-filled universe wouldn't be limited to gravity and the large-scale structure of the cosmos. Light itself, the messenger that allows us to observe and understand the universe, would be profoundly affected. You see, air molecules scatter light, a phenomenon known as Rayleigh scattering. It's the reason why the sky on Earth appears blue. Shorter wavelengths of light, like blue and violet, are scattered more strongly than longer wavelengths, like red and orange. In a universe permeated by air, this scattering would be ubiquitous, on a cosmic scale. Imagine looking up at the night sky, but instead of seeing a tapestry of twinkling stars and distant galaxies, you see only a uniform, opaque fog. Light from distant objects would be scattered in all directions, unable to reach our eyes or our telescopes. The universe, for all intents and purposes, would shrink to what we could see with the naked eye, a tiny bubble of local space. Astronomy, as a science, would be dealt a death blow. Our telescopes, both ground-based and space-based, would be rendered useless, their view obscured by the omnipresent cosmic fog. Our ability to study distant galaxies, to unravel the mysteries of dark matter and dark energy, to understand the evolution of the cosmos, and to search for other potentially habitable worlds, all of this would be lost, hidden behind an impenetrable veil of scattered light. And let's not forget the direct impact on life, particularly here on Earth. While the grand cosmic events we've discussed might seem distant and abstract, the introduction of air into space would have very real and devastating consequences for our planet. As we touched upon earlier, the increased friction in an air-filled space would lead to a dramatic increase in the number and intensity of meteor impacts. The Earth would be bombarded by a constant barrage of space rocks, ranging in size from small pebbles to large, potentially extinction-level event asteroids. Moreover, the friction between the Earth's atmosphere and the surrounding cosmic air would generate a tremendous amount of heat. This could potentially intensify the greenhouse effect, triggering runaway climate change and rendering our planet uninhabitable long before it was consumed by the expanding sun or crushed into the supermassive black hole. So, what have we learned from this rather terrifying, yet undeniably fascinating, thought experiment? We've seen that a universe filled with air, while seemingly a simple modification, would unleash a cascade of catastrophic events, each one more dramatic and destructive than the last. From the fiery demise of our solar system to the ultimate collapse of the universe into a singularity, the consequences are truly mind-boggling. It highlights the profound importance of the near-perfect vacuum of space, a seemingly empty void that is, in fact, a fundamental aspect of the cosmos, a necessary condition for the existence of everything we observe and experience. The vacuum allows stars to form and burn brightly for billions of years, galaxies to evolve and interact, and light to travel unimpeded across vast cosmic distances, carrying with it the stories of the universe. This hypothetical scenario also deepens our appreciation for the intricate balance of forces that govern the universe. The interplay between gravity, dark energy, and the initial conditions set in motion by the Big Bang has created a cosmos that is not only stable but also capable of supporting the evolution of stars, galaxies, and ultimately, life itself. So, the next time you find yourself gazing up at the starry night sky, take a moment to appreciate not just the beauty of the stars and galaxies, but also the profound importance of the emptiness that lies between them. If you enjoyed this mind-bending journey, smash that like button and share this video far and wide. And, of course, don't forget to subscribe to the channel and hit that notification bell so you won't miss any of our future cosmic explorations. And for now, farewell, fellow space enthusiasts.